Hi and welcome to this video where I'm going to be introducing you to the basic concepts associated with solubility and solubility equilibria. This is one of the cornerstones of this standard, so it's really quite important. So the first thing I really want to do is look at solubility, and some of you may have learned a bit about solubility in year 11 and maybe even in year 12, and you will have learned some solubility rules, which is that some things are soluble and some things are insoluble. So the first thing I want to tell you is to take that knowledge and remove it from your brain. I realise that's rather challenging, but it's actually really important because we don't talk about soluble and insoluble at this level. Okay, we're going to look today at what is solubility, why we don't need the solubility rules, and what solubility has to do with equilibria. So the first thing, when we talk about solubility, what we're talking about is how much of something will dissolve. What is the maximum concentration of a solute, that is a solid, that will dissolve in 1 litre of water at standard temperature and conditions. So 25 degrees C, 1 atmosphere of pressure. So we've got 1 litre of water, 25 degrees C, 1 atmosphere of pressure. How much of this solid is going to dissolve? That's our solubility. And a saturated solution is a solution that contains the maximum amount of dissolved solute. The other thing that's really important is the solubility product, which is the equilibrium constant that is based on the solubility of that salt. Okay, and that will make more sense in a minute, I hope. Okay, so soluble and insoluble. There's no such thing as insoluble. That's probably the most important thing to be aware of. There is no such thing as insoluble. I will repeat this, okay, because it's really important. Everything will dissolve to some extent. It's just that for some things that extent is very, very, very small. Okay, so everything is soluble on a continuum. There's a point where when something will no longer dissolve. So if you think about sodium chloride, it's something that we would traditionally consider as a soluble salt. You can, however, get to the point where you've put so much salt in a solution that no more will dissolve. Does that make it insoluble? No, it just makes it quite soluble. Whereas for some things, like for example lead hydroxide, the amount that will dissolve is very, very small. So we would call that sparingly soluble. And that's the term that we're going to talk about in this standard. We don't talk about insoluble salts, we talk about sparingly soluble salts. And I think that's really important to keep in mind. It's not insoluble, it's sparingly soluble. Okay, so when we talk about, for example, a lead hydroxide, the solubility is the maximum amount of lead hydroxide that will dissolve. So if we took a saturated solution of lead hydroxide, it would be the amount of lead hydroxide that is dissolved into 1 litre of water to make a saturated solution. So we can think of the dissolving of any sparingly soluble salt as an equilibrium reaction between the undissolved solid and the dissolved ions. Because if you can imagine it, and hopefully you will get an opportunity to do this or see this in class, you have a beaker with some solid sitting at the bottom and a saturated solution above that. So for any salt, we're going to call it AB, then when that dissolves in an equilibrium reaction, we will get a certain amount of A+ ions and a certain amount of B- ions. And the amount of A+ and B- will be directly related to the ratios of A and B in the salt. And then you can turn that into an equilibrium constant expression. Now the equilibrium constant is of course the concentration of the products divided by the concentration of the reactants, but we don't include solids or pure liquids in the equilibrium constant expressions because their concentrations are constant. So in this case, we simply have the concentrations of the products multiplied by each other, which is why we call it solubility product, because they're multiplied together. So this is the general format for any KS expression, and this is probably one of the ones that I really want you to learn, the relationship between the dissolving of that solid and the Ks expression. And if you learn it in this format, then it doesn't matter what type of salt you have, it doesn't matter what formula you have, you can do it with anything. Even something that goes beyond the scope of NCA level 3, if you're looking at scholarship, if you're at university, it doesn't matter, this process will work every time. Okay, so just relating the concepts of solubility and Ks, the solubility product. Remember that the solubility is how much will dissolve. Okay? Now that can be affected by a variety of factors, such as temperature, the presence of other ions, and all sorts of other things. So we all know that if you heat up water, then you will get more salt dissolving, right? There are other things that can affect it too, and anybody who's played around with the old iron standard knows that when you change the pH of a solution or you add extra ions into it, then it can change the solubility. However, the solubility product, Ks, is actually a constant. It doesn't change. It doesn't change unless you change the temperature. I should say temperature can affect Ks just as temperature can affect any equilibrium constant expression. But otherwise you can simply look up values of Ks in a data table and away you go. So just to be really, really clear, Ks is a constant, but the solubility can change. Okay, that's really, really important to be aware of, because a lot of this topic will involve you figuring out how the solubility changes when we change certain factors. Okay, so just to give you some examples of Ks expressions. Okay, it's always the concentration of the products raised to the power of the number of each of those products. The square brackets mean concentration of. So if we take copper hydroxide, which breaks up, it's sparingly soluble, so a small amount of it dissolves to form copper ions and hydroxide ions. Our Ks expression is simply the concentration of the copper ions multiplied by the concentration of the hydroxide ions squared. Hydroxide ions are squared because there are two of them. Other examples, barium sulfate there, so it makes barium ions and sulfate ions. And there's the Ks expression, silver chromate. Now the biggest trick, or one of the things in this standard, you must know the charges on basic ions. So anything in group 1 must have 1+ charge on it. Anything in group 2 must have a 2+ charge on it. And you should know the concentrations of those basic polyatomic ions. So if you think of that level 1 ion table that you got given way back when, you should know that. You should be able to recognize the ions and you should know the charges on them. And from the charges on the ions, even if you don't know all of them, for example, you might not know barium, but you should know that sulfate is 2-. You can look at that formula and go, it's a 1-to-1 ratio, therefore barium must be 2+. Okay? So there has to be a certain amount of chemistry knowledge and logic that you can apply to these problems. Similarly, you might not know the formula of or the charge on the chromate ion, but you should know that silver is +1. If you've got 2 silvers, that's 2 lots of 1+, therefore the chromate must be 2-. Okay, this is level 1 chemistry stuff, guys. So if you don't know it, go out and learn it before I see you back in the next video where we start looking at some calculations using Ks. I'll see you there.